The next two videos are about graphs. Just going to be defining concepts, looking at graphs. Graphs are a topic that come up all the time in computer science, and they're really important. So in this first video, I'll just be giving us the general feel of them using three examples. In the next video, I'll be talking about particular special classes of graphs that people might care about. I want to be really clear up front. Well, a lot of people, when they think graph, they think what we have here on the right? These sort of like plots of numeric data, and I cannot emphasize strongly enough that I am not interested in these. No way, Jose. That is not the kind of graph that I'm talking about. The kinds of graphs we're talking about are a little different. They're graphs with nodes and edges. Let's start writing down some key terms that we'll need. Whoa, let's write them down in a legible script. Nodes, edges, and we'll sort of see what all these terms are in a bit. So I want to go over three examples: graphs of maps, graphs of social networks, and call graphs. Right? All of these are topical things. They're things that are important to computer science, and many of them are things that you've already used. So I want to start with the OG, Leonhard Euler, who's kind of like the creator of graph theory. He seems like a pretty funny, chill dude from this picture too. Like, A, what is going on with that hat? B, love the ruffle. It's like a subtle thing. The stripes are a good look. And then C, like the facial expression to me says that this is a guy who like enjoys a good joke. Anyway, Leonhard Euler. He's a big deal. You might know him from calculus already. He came up with a bunch of interesting stuff there too. But he also is kind of the creator of graph theory as we know it. So one of his famous problems was called the Seven Bridges of Königsberg. So what is Königsberg? Well, now it's called Kaliningrad, and it's an exclave of Russia, which is just like a whole weird geographic thing. I urge you to just Google it. You can look up the history. It's just strange days. World War II was a hell of a time. Okay, but what he pointed out was that like in the middle of the city, let's zoom in real close, there's these two islands, right? And then like right here, there's some church that people care a lot about, Cathedral of Königsberg. And then this is the airport now, I think. Yeah, I'm guessing that's an airport. Maybe it's stadiums. Who even knows? And then there's bridges between all of these. So in his day, the bridges were a little different. If you go to the Wikipedia article on this, you'll see this. But what you can notice is like, look, so what happened? So there's like a point here for this island. There's a point here for this island, and then here's one bit of the mainland, and here's one bit of the mainland. And then how could we go, right? Like, let me get a slightly finer pen. We could go from there to there. We could go from there to there. And we could go from here to here, right, via that bridge. This bad boy could go in down this way. Could also go in over this way. Here we've got a couple of options. Right? And then what it is my man Leonhard was really into going in on long walks in the city. And he wanted to know, like, hey, if I start, say, here, oops, that's too big. If I start here, can I walk? Visiting all of the spots, going over every bridge once, but never more than once. Right? He wanted like an interesting walk, right? Can I have a nice loopy walk? No repeats. And so to do this, he realized that what he ought to do is abstract his notion of graph. So let's pull that out a little bit. So what he realized was like, well, look, let's just look at it this way. We've got the different points, and then we have some set of edges between them. Whoa, nobody wanted. So, oh, stop. You really need to stop. Thank you. right? So this is what he ended up drawing, and this is the mathematical object he thought about because the map was too complicated. Okay, so now we can introduce some terminology. This is a node. This is an edge. Okay, so this is kind of how graphs started, just as an abstraction for reasoning about the connections, the relationships between different things. So nodes are the things, and edges are the relationships. Let's write that down in our little translation chart we const up over here. So nodes, things, edges, relationships between things. Okay, so that's the general idea. It's just a super useful, super general abstraction. So another thing that graphs get used for are social networks. So I've chosen some familiar characters. We've got Big Bird, we've got Cookie Monster, we've got Oscar the Grouch. He was always my favorite. Maybe Cookie Monster, and then maybe Ernie as backups. Tough call. You don't want to have to choose. The Count. Little pedantic, to be honest, and the Snuffleupagus. You may not know these characters if you didn't watch Sesame Street. Sesame Street's still a hoot, I think, even for adults. It's pretty funny. But so one way to think about a graph is to say it's a social network. What do we mean by that? Well, the objects are people or other social entities, and the edges are relationships that those people have, friendships, sending a message, sending a payment, beating in arm wrestling. Like, who knows what it means, right? So it depends. Now, it also kind of depends in that, like, relationships can be one way, right? This is a sad truth of our world. They're like, okay, Big Bird and Snuffleupagus see each other and know each other, but nobody else can even see or know Snuffleupagus, though I think there's a later episode where they establish that Snuffleupagus is actually real. Big Bird and Cookie Monster might be buds. And then look, Big Bird is friends with Oscar the Grouch, but it's not necessarily fair to say that Oscar the Grouch is friends with Big Bird, right? Like, Oscar the Grouch is kind of a grouch, right? Cookie Monster might also be friends with Oscar the Grouch, but Oscar the Grouch, like, okay, we'll be friends because you might give me cookies, and, like, I may not be happy about stuff, but at least I've got cookies, right? And then the Count may not know Big Bird, but is friends with the Cookie Monster because you got to count your cookies. And he's just like, he's annoyed. He's not even friends with Cookie Monster anymore either. Right, hypothetically speaking, such is a social graph. So one difference between the graph we drew here and the graph we drew for the bridges of Königsberg, the bridges in Königsberg, in Kaliningrad, you can go either way on a bridge, at least on foot, usually, right? Sometimes cars can only go one way or whatever. But social relationships here are definitely directed, right? Like, maybe you're friends with someone else and they're not friends with you. That's a sad way to think about it. Maybe you've sent someone an email and they haven't responded to you, right? So then there's just this asymmetry. So what it is these edges may be directed or undirected. Right? So this is a directed edge one way, and then this is a directed edge as well, but it's two-way. Okay. One last example from the domain of computer science, call graphs. So here's the code for Levenstein. And we might be interested in, say, compiling the code or just reasoning about the code, thinking about it, or wanting to know why it's slow. So we just want to know which functions call which other functions. Super common activity. So what people build is what's called a call graph. So what we'll do is we'll create a node in our graph for each function, and then we'll have an edge from that function to other functions that they call. So let's do it. So we'll have a node, Levenstein. I'm going to ignore the inner here and call it just part of Levenstein. So it, for example, calls add edit. Right, that's happening right here in this case. It also calls delete edit. Okay, over here, it calls EQ base. Over here, it calls itself, so I'm going to add this edge. This is called a self loop. Right? It's an edge from a thing to itself. Okay, some relations can work that way, some don't. For example, if we were doing a social network and we had the friend relation, are people friends with themselves? Maybe yes, maybe no. I definitely know some people who aren't, I would say, on friendly terms with themselves, though that's probably a thing they need to work out. Okay, cool. If we want to be super pedantic, right, I said we wouldn't count it, but, we have inner, which calls itself, but also calls Levenstein. Right, Levenstein calls one other function. Oops, sorry. Argmin3. You'll notice none of these functions call back to Levenstein. Both add edit and delete edit call map. And then Argmin3 here is going to call LEB. It's also, because it's in higher order in this setting, it's also going to call total cost. And total cost is going to call cost, and it's also going to call plus. So you may wonder, like, wow, Levenstein was hard to think about. That was tricky to do proofs about. And like, this call graph in part explains why. Right? That's a lot of crap. That's a lot of stuff to think about. Right? But it's very common for people to draw call graphs like these to sort of suss out the performance issues or just even the way that a piece of code works. Right? This is a very common way of thinking. Okay. So there's a self loop. Right? There's such a thing as self loops. Oops. And there's one other thing that I want to highlight that I didn't remark on over here. Here we have multiple edges. Right? These two nodes, this node and this node, has 1, 2, 3 distinct edges between them. Right? Most graphs don't allow multiple edges, but some graphs do. It's a thing that happens, right? So far here on the lower left, we've got sort of the key things you need to know about for a graph, right? So you're going to have some nodes. It's going to be a set of things, right? And then you'll have edges, right? And you might or may not have multiple edges. If you don't have multiple edges, right? If you don't have multiple edges, then you can think of it as a set, but otherwise it's something else. Self loops determine whether or not things can have edges to themselves. And then these edges can be directional or not. You might interpret them directionally or not. Okay, so I want to conclude with talking a little bit about the formal model and then some other important concepts that we'll get at a little more in later videos. Model. Nodes is a set V. V for vertex, which is just another name for node. Okay, this is the mathy model. Edges are a relation on pairs of vertices. So this is perfect for, this model is perfect for directed, single-edged, allowing self-loops. If you want to allow multiple edges, right, so this is problematic if you want to do a slightly different graph. Multiple edges can't be a set. So you could say it's something like V cross N, the number of times such edges occur, or something else, right? You have to build a different model if you want it to be formal. If you want no self loops, so this is a set E, typically is the name of that set. If you want no self loops, then you just make the requirement E not just not reflexive, anti-reflexive. That is, n is not in E for all n in V. But you just have to make that requirement. Okay, and then last and most problematic, undirected. Okay, then you just have to say, okay, well, E symmetric. Right, because if we have N1 and 2 in E, then it should really be the case that you can have the other edge. Right? The formal model of these simple graphs is just really inconvenient. So what people tend to do is not think about it too hard. They just sort of say, like, look, we all know what we mean by an undirected graph here. But if you try to think too hard about it, you'll see that the definitions are actually really complicated and very subtle here. Okay, but as a general rule, this is the good enough model. Right, this is how people will really talk about it. This is the standard thing. And then these issues are subtleties that people will bring up as needed, but kind of avoid as mostly just being inconvenient. Okay, there's a few other concepts I want to talk about that are important. So one concept is degree. Number of edges going in or out of a node. And then people will also talk about in degree for just in, or out degree for just out. Okay, so let's go back to our social network. Okay, so the degree Snuffleupagus, something like that. Okay, that's just 1, depending. Well, probably it's actually 2. 1 in, 1 out. Big Bird has 1 in, 1 out, so we're at 2. 1 in, 1 out, we're at 4, 5. So degree in is 1, 2. Degree out is 3. Okay, you can compute degrees over here also. For simple graphs or undirected graphs, there's no such thing as in or out degree. There's just plain degree. For these call graphs, we can look and see that okay, map has in degree 2 and out degree 0. Add edit has in degree 1, out degree 1, and so on. Right? Okay. So that's the concept of degree. Path is just a trace of edges. Typically, what people will do is just name the nodes. If you have multiple edges, that's a little more subtle. Simple means no repeated nodes. Okay, circuit is a path. Oops, let me do it in the same red so that it all matches up. A path that ends where it starts. And then simple, no other repeated nodes. Right, and there's a couple other genres of paths and circuits that people care about. These are just sort of things to know about. So a circuit is a loopy path. A path is just a trip you can take starting at one node and following edges to get to others. That's the entire gist of it. Not a lot else going on. So there's a bunch of terminology here. It takes a minute for it all to get sorted, but I find that this stuff is generally pretty intuitive, right? this may not have been your mental model already, right? You might not have had an object that looked like this in your mind of graphs, but it's one that I think that you'll adapt to very quickly, right? It's a very easy metaphor for the world. If you have any questions about any of the terms I used here, or you know other terms and you're not sure how they relate, please feel free to mention those on Piazza. I'll have one more video coming for you just talking about special classes of graphs that people care about in particular, and that'll be my last video for you for the year. It's been a real pleasure. Hope you're all doing good. All right, so long, y'all.